hours. So
Okay, no problem. Tell me the last topic, what we had done.
we
I think
did
it was
system and surrounding.
okay. Now, next is about thermodynamical laws, in which we first define what do you mean by zeroth law. It simply defines about concept of temperature.
Sure.
Okay, so on the basis of this, let me define you. Suppose you have any system. This particular wall is called adiabatic wall, which having ability to restrict any flow of heat through it. So you will say, no heat can exchange through this particular wall. But this particular wall is diathermal, which means it allows exchange of heat. Exchange heat through it. So suppose we have three different thermodynamical systems. Let's say this is A, this is B, and this is C, all having different temperature initially. So if they are connected like this, so you'll say there will be heat flow between A and C, that is through this wall from this point to this point. And similarly, there will be flow of heat between B and C through this wall from this point to this point. Is it clear?
Yes, sir.
This particular flow of heat between any two thermodynamical system will define up to which till they acquire equilibrium temperature. So there will be flow of heat between A and C till they acquire equal temperature. Similarly, there will be flow of heat or transfer of heat between B and C till they acquire equal temperature. It means at thermal equilibrium, when temperature of A and C becomes equal, there will be no further flow of heat. And similarly, in thermal equilibrium between B and C, there will be no flow of heat between B and C through this particular wall. So it says, if two thermodynamical system, A and B, is individually in thermal equilibrium with third system, that is C, so they must be in equilibrium with one another. Is it clear?
Yes, sir.
So from this part, we can state when two thermodynamical system is in equilibrium or is in thermal equilibrium with third system, then there must be in equilibrium with one another. It means if temperature of A becomes C, that is thermal equilibrium, and temperature of B becomes equals to C, then we can say A and B also will be in thermal equilibrium with one another. So in this entire part, we can say temperature is the physical quantity which will be responsible for flow of heat from one body to another body due to their temperature difference till they acquire equilibrium temperature. Is it clear?
Yes, sir.
That's why zeroth law simply defines about concept of temperature, since temperature is the physical quantity which will be responsible for the flow of heat between two thermodynamical systems. So we can state from this part, temperature is the physical quantity responsible for exchange of heat between two thermodynamical systems till they acquire thermal equilibrium or equal temperature. Any doubt related to this entire concept of zeroth law?
No, sir.
Okay, just write it down.
Done, sir.
Now, next is first law of thermodynamics. It's simply defined conservation of energy, or you can say it is based on conservation of energy. Suppose you have a vessel containing gas and with movable piston, let's say this, having gas, so if heat is supplied to this particular system, this heat supplied to this particular system may be utilized in two different processes. First, to change the internal energy of system, and second, to do some work on this piston to expand it from this level to this level. Similarly, if heat is being ejected out from this particular system, so this heat being ejected out must compensate two different factors to change internal energy and to do some work on this particular piston to compress it from this state to new state this. So we can say from this entire part, the heat supplied or ejected from this particular system must be utilized in two processes. First, to change the internal energy of gas, and second, to do some useful work, either in expansion of gas or either in compression of gas. Is it clear?
Yes, sir.
That's why it is based on conservation of energy. So state energy neither be created nor it be destroyed. It simply transforms from one form to another. So on the basis of this, we may define about heat flow, change internal energy, and work done as the amount of heat ejected or supplied to the system can be utilized in changing internal energy as well as doing work. So from this part, we can say dq equals to du plus dw, where dq is heat supplied or ejected, du is change in internal energy, and dW is simply work done. Fatima, any doubt?
No, sir.
Okay, just write it down. Then I'm defining the property of these three different terms.
Done, sir.
Any doubt related to this part?
No, sir.
Okay, so we have mainly three different terms: heat, internal energy, and work done. So mainly divide these three different terms into two broad categories depending upon their property. First is called state function. Those physical quantity which depends upon initial and final state of gas, it will be independent of path followed by the gas, are termed as state function. I'm giving example. So it will be either internal energy or entropy. So simply state function is the physical quantity which depends upon initial and final state of gas. It will be independent of path followed by gas is called state function. Is it clear, Padma?
Yes, sir. But what's entropy?
Entropy I will define you later. You must have done about entropy in chemistry as well. Entropy simply defines you randomness, calculation of randomness, or you will say the amount of heat energy that will be unavailable for the conversion of mechanical energy or work done is termed as entropy. Okay.
Okay, sir.
So change in internal energy is du is equals to N times Cv into dt. Cv is molar specific heat at constant volume. If you further expand it, you will get N times R divided by gamma minus 1 into dt. In terms of degree of freedom, it will be equals to N into F divided by 2 times R into dt. Further, in terms of PV, it will be equals to PV is equals to nRT. So F by 2, or simply P initial V initial minus P final V final divided by gamma minus 1. So according to different problem, we may use these different expression to find internal energy. Now, let me define you the sign convention. If temperature of system increases, so internal energy will be taken as positive. If temperature of system decreases, then internal energy will be taken as negative, or simply vice versa. You will say if internal energy is positive, temperature of system will increase, and if internal energy becomes negative, it means temperature of system will decrease. Is it clear?
Yes, sir.
Now, depending upon this, you'll be asked question like, suppose you have any thermodynamical system in cyclic manner like this. Let's say this is pressure versus volume curve and graph is cyclic. So you'll be asked, what will be change in internal energy for this particular process? So just think on what factor change in internal energy depends upon. So you'll say it simply depends upon initial and final state. So let's say this is initial state. So on complete roundup, you get this particular point to be final state. It means both initial and final point is at same. So difference of these two terms will get 0, I think. So you will say change in internal energy for any closed path is also equals to 0. Is it clear?
Yes, sir.
This is sign of integration, simply defined for summing up of term. And if there is representation like this closed loop, so it will be termed as closed integration or integration over closed loop, we can say. So from this part, we can say, since initial and final point for this particular process is same, so on taking the difference of these 2 points, you'll get 0. It means for any cyclic process or any closed path, change in internal energy will be always 0. Is it clear?
Yes, sir.
Now suppose we have another term. Gas is going along this way, and along this way. Let's say this is path first, this is path second, and this is path third from point A to point B. So you'll be asked, what will be the change in internal energy, or what will be the relation between change in internal energy for all of these 3 different paths? Which one will be more or greater, or which will be smaller, or what will be the relation between these 3 different internal energy according to this process? So to define this, just think on what factor change in internal energy depends upon. You will say it simply depends upon initial point and final point. Is it clear, Fatima?
Yes.
So we have same initial and final point for all of these three different paths, we can say.
Yes.
So on taking the difference of final minus initial for all three different paths, will it be same or different?
We say
Good. So we can say change in internal energy for all these three different paths will be equal to each other. Any doubt?
no, sir.
Okay, just write it down. Just write it down. I'm just coming in 1 minute, okay?
Okay, sir.
Fatma, done?
1 minute, sir.
Okay.
Done, sir.
Okay. Next is path function. Those quantity which depend upon path followed by the gas, it will be independent of initial and final point only, are termed as path function, such as heat, supplied or rejected, and work done. So the physical quantity which depends upon path followed by gas is termed as path function. You must have learned about conservative force and non-conservative force in chapter 6th. Fatma, any idea?
Yeah, yeah.
Just tell me about conservative force. Conservative force are the force for which work done is path independent. It simply depends upon initial and final point. Similarly, in this path, we can say about a state function, the quantity for which simply depends upon initial and final point of gas are termed as state function, just like conservative force. For non-conservative force, work done will be path dependent. So path function, the physical quantity for which it may depend upon path followed by the gas, is termed as path function. Is it clear?
Yes, sir.
Okay, so first is how to calculate heat. So dq equals to n times c into dt, where n is number of moles and c is molar specific heat related to that given process. So on the basis of which you will be able to calculate heat supplied or ejected from this particular system. So on the basis of it, we may define sign convention. If heat is being supplied to the system, then it will be taken as positive. And if heat is being ejected out, from system, then dq will be taken as negative. In this part, we have C is molar specific heat constant related to that process. If you are using isobaric, that is at constant pressure, so C will be Cp. If you are using isochoric, so C will be Cv. If you are using isothermal, adiabatic, so C will change according to the process which we are calculating in. Is it clear?
Yes, sir.
Okay, just write it down. What is N here?
Number of molar.
Good. Number of moles.
Done, sir.
Now, next is how to calculate work done. Work done is simply equals to force times displacement. We may write force in terms of pressure as pressure into area of cross section into displacement. Now, this quantity, area into displacement, or simply area into length, is termed as volume. So it will be equals to integration of P times dV. So depending upon different process, you will have different amount of pressure and in relation with volume. So on putting the values of these two terms and integrating, you will be able to calculate net work done related to those different processes. So in general, I'm defining you how to calculate work done and what will be its sign convention. Suppose we have piston initially at this point, and in this point initially and this. So if work is done on the piston, so it will tend to expand it from this initial volume to some final volume towards this. Similarly, if work is done on the piston by any external agency, so it will tend to compress gas from this state to this state. So let me define you the corresponding variation related to graph. Let's say this is P and this is V, pressure versus volume graph. According to this relation, which is nothing but product of any two different quantity, that is pressure and volume. So product related to graph will define you area under the graph. So from this part, we can say area under pressure versus volume graph will gives you work done related to that process. Fatima, is it clear?
Yes, sir.
So from the first part, let's say initial state of gas is at this point. So on expansion, volume will increase and correspondingly, there will be change in pressure as well. So let's say reach to some B point along path this. So if you draw a vertical line, so it will be its initial volume and it will be its final volume. If you further draw this particular curve or direction of arrow, you will get a clockwise notation of this particular curve. It means area under this particular graph will define you work done related to this process. So in this part, we can say first, final volume is greater than initial volume since piston is expanding from some initial volume to some final volume. So change in volume will be positive and hence work done will be positive. Next, during this process, gas is expanding. So we can say expansion of gas. Next, work is done by the system, that is gaseous particle on the piston to expand it. So we can say work is done by the system. By the system means by the gaseous particle on the piston. And the notation of graph for this process is in clockwise direction. Fatima, is it clear?
Yes, sir.
Okay. Similarly, we may define the next process. In this part, we have work done on the piston for which gas is compressing down. So curve related to this process will be like this. From this point A to some point B, variation of pressure versus volume. So it will be its initial volume, VI, and it will be its final volume, VF, and direction of curve will be along this way. So if you proceed this particular direction, it will look like an anti-clockwise curve like this. Is it clear?
Yes, sir.
So from this part, we can say final volume is smaller or greater than initial volume. Fatima, volume is
Yes.
decreasing or increasing?
It's decreasing.
Good. So difference of volume will be taken as negative, and hence work done will be negative in this case. Whether compression or expansion of gas is taking place in this process?
Yes.
Compression or expansion?
Compression.
Good. So we can say compression of gas. Next part, work is done on the system or by the system?
On the system.
Good. On the system by any external agency to compress it down. So we can say work is done on the system, due to which the notation of graph is in clockwise or anti-clockwise?
Anti-clockwise.
Good. So we mainly have 5 different information related to this entire process for expansion part as well as for compression part individually. Okay, any doubt?
No, sir.
Okay, just write it down.
Done, sir.
Now, related to this process, you'll be able to calculate work done related to any different part. Let me give you a question. Find net work done. This is V naught, and this is 2V naught, 3V naught. This is pressure V naught, 2P naught, and 3P naught. Let's say this is pressure versus volume graph. Like this. So you'll be able to calculate, find net work done related to this entire process. Let's say this is A, B, C, D, and this is point O. First, if you have to calculate work done for triangle AOD, work done is simply equals to area under pressure volume graph, we can say. Is it clear?
Yes, sir.
So how to calculate area under this particular triangular region? Or what would be the formula of area of triangle? Fatima, tell me the formula of work done for, or simply area under triangular region. How to calculate?
Area of triangle.
Area of triangle is equals to?
1/2 into B into H.
Good. So 1/2 base we have in this part is AD, and perpendicular we have this vertical region, that is 2P2 minus P2, P naught. So base we have 3V naught minus V naught, and for this perpendicular we have 2P naught minus P naught. Is it clear?
Yes, sir.
The notation of graph is in clockwise or anti-clockwise? Just A or D?
Anti-clockwise.
It is going along this way. Is it clockwise or anti-clockwise?
Clockwise.
And work done along clockwise is taken as positive or negative?
Negative. Oh, sorry, positive.
So it will be termed as positive. Just simplify it. Half 3 minus 1, it will be 2 times of V naught. And 2P minus P, it will be just P naught. So 2 and 2 will cancel out. So you're left with just P naught, V naught. Is it clear?
Yes, sir.
Similarly, if you have to calculate work done along BOC. So again, it will be area under the triangle. So it will be half base into height. Tell me the value of base, that is BC.
3p0.
No, it is going along this way. From this part to this part. So 3v0 minus v0, okay? That is horizontal component.
Okay.
And what we have for vertical line from this point to this point, it's 3p0 minus 2p0. Is it clear?
Yes, sir.
Now check the notation of direction of curve. Is it clockwise or anti-clockwise?
Anti-clockwise.
So work done in anti-clockwise taken as negative or positive?
Negative.
Good. So if you simplify it, minus 1 by 2, 3v0 minus v0 is just v0, and 3p0 minus p0 is just p0. So 2 and 2 will cancel out. So you're left with minus of p0 p0. Is it clear?
Yes.
So net work done will be sum of these two terms, that is work done along AOD and work done along BOC. So work done we have along AOD as positive of V0 V0, and work done along BOC is minus of P0 V0. So on adding these two terms, you'll get 0. It means net work done for this entire process is 0. Is it clear?
Yes, sir.
Okay, just write it down.
Done, sir.
Okay. Any doubt after this part?
No, sir.
Okay, so let's stop here for today. Just revise this entire part and try to solve assignment related to this. Okay, we'll continue in next class. Okay,
Thank
then.
you, sir.
Thank you.
Bye.